Hello and welcome to the 35th lecture of this short course called Behavioral Theory of Systems with a View Towards Data Driven Control. If you remember, we were in the middle of proving conditions, sufficient conditions under which we have this, where let me remind you that this is the Aleph Hankel matrix created from a finite time series W, yeah, and we are assuming that W is coming from a behavior, underlying behavior B given by some kernel representation which we do not know yet. We would like to find this out. Yeah, the trick of finding out left kernels of these Hankel matrices. Yeah, the trick works in this particular case of finite time series when this is satisfied. Yeah, we were in the process of finding out conditions on the data which will guarantee that this happens. And if you remember in our attempt to get these conditions, what we did was the following. Let me just go back to this previous slides. So that we can have a relook at the conditions. Okay, what was it? So we said that, okay, if we have, so first we assume that, okay, suppose this is not true. So in general what happens is, if you remember, the column span of such a Hankel matrix constructed from the finite time series is always contained in this BL, the L restricted behavior, and therefore the left kernel of this guy will in general contain BL pub. So what we assume that, okay, suppose this containment is strict, yeah, then there will exist some R vector in the left kernel which will be here, but it will not be the corresponding R psi will not be there in BL pub, which is also the same as the Lth or the Lth degree annihilating polynomial vectors. It will, because this is a strict containment we are saying, so we should be able to find out such a vector, right? And then we started to construct some method by which we would be able to show that this leads to a contradiction. And what was that? So I said it's best to go to a situation when things have settled down, namely if n is the order of the system, that means the number of state variables in a minimal state space representation, we go to this L plus n size, and not size, the L plus n order of all Hankel matrices and stuff. So if we look at this H L plus n W, yeah, so same from the same finite time series data, suppose we construct this H L plus n W matrix, okay, then obviously the left kernel of this matrix once again will contain B L plus n pub, right? But at the same time it will also contain something more, something that comes from this guy. You see, R is there in the left kernel of HL, and when you go to HL plus 1, it's actually you are adding further and further rows below HL to get this HL plus n. And we have already seen that for Hankel matrices, because of their very structure, it so happens that if there is a vector in the left kernel of a smaller Hankel matrix, as you add newer rows, those newer rows also will satisfy a similar equation, yeah, coming from that particular left vector in the left kernel. What you have to do is you just have to keep shifting that left kernel, right? I mean, keep shifting that vector in the left kernel. In other words, this R xi that was there in the left kernel, I am sure you are able to figure out why I am writing r xi instead of just a vector. I have just made this identification implicitly, yeah, that h l plus n is in fact identifiable with things which are polynomials. So that this is the polynomial. If you are feeling flustered, just remember that if you have r0 r1 dot 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 up to rl, this row vector is identified with r0 plus r1 xi plus dot 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 up to rl xi, and we call this guy as r xi. This identification is 1 to 1, so therefore I can say things like this. So what we were saying is that because r xi is in this left kernel of hl w, it follows then that r xi will also be in the left kernel of hl plus n w. Not just that, xi r xi will also be here, dot 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 up to xi to the power n r xi will also be there, yeah, in the left kernel of hl plus n. Let me rewrite this properly because I made a mess out of it. R xi in the left kernel of hl w implies r xi r xi dot 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 up to xi to the n r xi, all of them will be there in the left kernel of hl plus n w, right? And you can check that these are polynomial. If you write them as polynomial row vectors, they have degree at most s plus l plus n, and this is indeed true here also, because you see this had degree less than or equal to l. When you multiply by xi to the n, the degree can go only up to n l plus n, not more than that. So therefore that way also it matches. Yeah, I hope you understand. This is happening because of that shifting property, right? When you have a smaller Hankel matrix, when you have a left kernel vector in the left kernel, then you get a bigger Hankel matrix. You shift that left vector in the left kernel, you still have that vector in the left kernel. That is why this is happening. Now because of that, it so happens that the left kernel of the L plus nth Hankel matrix will contain not just be L plus n perp, but also the vector space spanned by r xi times r xi dot 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 to xi to the power n r xi. I made a slight mistake in calculation in the last lecture. This vector space, of course, I said dimension n, but I was wrong. You see how many vectors are there? Linearly independent vectors, and n plus 1 number of vectors are there. So this dimension is actually n plus 1. Okay. On the other hand, dimension of B L plus n perp, as we have seen before, will come out to be equal to L plus n plus 1 times P minus n. Okay. Now, so the claim that I said was that, okay, the claim was that B L plus n perp intersection this vector space spanned by xi r xi dot 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 up to xi to the power n times r xi, this intersection is non-zero. That was the claim, and we said that under this claim we actually get a contradiction. Yeah, we actually get a contradiction to the fact that r xi belongs to this, but r xi does not belong to this. This is contradicted. We get a statement which is contradictory to this one, provided the claim is true. That is what we proved in the last lecture. If the claim is true, then we reach a contradiction. Right, and we want to reach that contradiction to prove that what we had assumed is wrong, that is, this assumption is wrong, this assumption is wrong. We need to achieve a contradiction to say that this assumption was wrong. So to make sure that the contradiction is achieved, we have to figure out a reason why this claim should be true. Yeah, it may sound a little confusing here. We are trying to prove that what we had assumed is not true. Yeah, so therefore, in order to reach that contradiction, yeah, we need to show that we need to figure out conditions under which this should be true. Okay, right. Now, when is the claim true? Let me just go ahead with this, and we'll see that this will be that the things are becoming clear. Okay. Now, okay. So, if the claim was not true, suppose there was no intersection between the two. Suppose B L plus N perp intersection R xi R xi xi to the power n R xi. This is equal to 0. If this is equal to 0, then this is actually a direct sum because their intersection is 0, and therefore the dimension of this guy will be just the sum of these two. What is this dimension? This is L plus N plus 1 times P minus N. And what is this dimension? This dimension is N plus 1. So this will cancel out, and this dimension will turn out to be equal to this. So dimension of B L plus N perp plus R xi R xi dot 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 xi to the n R xi, this dimension is equal to L plus N plus 1 times P plus 1. Okay, but this vector space B L plus N perp plus R xi dot 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 up to xi to the n R xi. This vector space is contained in left kernel of H L plus N W, right? So therefore, dimension of left kernel of H L plus N W must be bigger than or equal to L plus N plus 1 times P plus 1, right? Because this vector space is contained in this vector space, so this dimension must be bigger than or equal to this number, which is the dimension of this guy, the left hand side. Okay. Now, by rank nullity theorem, however, dimension of the left kernel of H L plus N W is equal to L plus N plus 1 times P plus L plus N plus 1 times M. That is the total number of variables W, right? That many variables are there, and each block is of this, each block is size P plus M when you write down that Hankel matrix. And how many such blocks are there? Precisely equal to this plus 1. That is why this is the total number of, this is the number of rows in this matrix, okay, minus rank, because I am looking at left kernel. By rank nullity theorem, rank of H L plus N W, that's this dimension by rank nullity theorem. Is it okay? Right. So by that we then have L plus N plus 1 times P plus L plus N plus 1 times M minus rank of H L plus N W. This is bigger than or equal to L plus N plus 1 times P plus 1, right? That was the number, yeah. So this and this will cancel out, okay. So then what we are left with is rank of H L plus N of W, yeah, of W, if I take it to the other side, had better be less than or equal to, sorry, L plus N plus 1 times M minus 1, right. Now this is what we can play around with, okay. This is what we can play around with. What we are going to say is, see here this M is appearing, no. So this is the condition that we are going to put in. This is very important, absolutely important, huh? Condition. I put this condition on the input of the system U, and I say that this input, this rank, is equal to L plus N plus 1 times M. What this means is that this H L plus N, this Hankel matrix, L plus nth order Hankel matrix created out of the input only. The L plus nth order Hankel matrix created out of the input only if this is a full row rank matrix. Yeah, when this happens, I say the input U, the input signal U, which is a finite time series, this finite time series input signal U is persistently exciting of order L plus N plus 1, the number of blocks, yeah, the number of blocks that are there. If H L plus N U is full row rank matrix, any signal, if you take any signal, yeah, any finite time series, and you create a Hankel matrix out of it, yeah, let us say the whatever order Hankel matrix out of it, if that Hankel matrix is a full row rank matrix, you call that signal to be persistently exciting of the order exactly equal to the number of blocks, yeah, which is exactly equal to this order plus 1, okay, remember. So once again let me repeat, U, the signal, is said to be persistently exciting of order whatever you call it, say delta plus 1 if H delta U is full row rank, okay. Now let us see how things will unfold the moment we make this assumption. So now we are going back to our condition before, the things that we were trying to prove. We are trying to find out conditions under which we have this, yeah, under which we have this condition. Problem is to find out conditions under which this is true, okay. Right. So let us go back. So we want to find out when is column span H L W equal to B L. Our theorem is the following theorem. Let B be controllable. We need that, remember, because the underlying image, underlying kernel representation was assumed to be full, was assumed to be factor left prime in order for us to derive that the contradiction from the claim, okay. So that is why we need B to be controllable. Let B be controllable. Further, let the input u be persistently exciting of order n plus L plus 1. You see, I know this L, but I don't know this n, a priori. We have to assume that we know and we have some information about this n, yeah, in order for this to be applicable. But we'll come to that later. But let us, for the time being, because we're trying to prove this theorem, yeah, which is not to say that we are devising a method, but suppose we are trying to figure out a condition under which this will be true, a condition under which we can actually work with a finite time series. We do not have to deal with infinite time series and infinite Hankel matrices. So, let B be controllable and let the input u be a signal which is persistently exciting of order n plus L plus 1, then that should imply, these two things together should imply column span of the Hankel matrix created, the Lth order Hankel matrix created of the finite time series data is in fact equal to the columns span all possible trajectories restricted to L of the given behavior, of the underlying behavior. That's the main theorem. That's called the fundamental lemma of data driven control, right? Okay, now let us see how this happens. So because, so sketch of the proof, yeah, we have seen every bits and pieces of this proof, in smaller pieces. We are now going to actually put together these pieces like a jigsaw puzzle. So first thing we notice is that because of persistence excite, because the input u is persistently exciting of order L plus n plus 1, we have the following, that rank of H L plus n u is exactly equal to L plus n plus 1 times m, which then means rank of H L plus n w must be bigger than or equal to L plus n plus 1 times m, right? Because notice that this is a part of this matrix. Yeah, to these rows, if you add the rows corresponding to the output y, you get this matrix. Yeah, let me write this down for you. H L plus n w in fact is a permuted version, row permuted version of H L u, L plus n, and H L plus n y, right? That's why you have this. Okay, now if this is so, this is one condition, and if B L plus n perp intersection r xi dot up to xi to the n r xi is 0, then that implies rank of H L plus n w. Remember, when this intersection is 0, we have this, we have this condition, this condition, okay, this condition, which also further implies that this rank must satisfy this. So if this were also true, then rank of H L plus n is bigger than or is so let me write down one step after the other, because we have done this thing a little earlier, it may have slipped our mind. This implies dimension of left kernel of H L plus n w is bigger than or equal to L plus n plus 1 times p minus n plus 1 this cancels out, but this dimension is equal to L plus n plus 1 times m plus L plus n plus 1 times p minus rank of h L plus n w. This must be bigger than or equal to L plus n plus 1 times p plus 1. This cancels out, which implies rank of h L plus n w must be less than or equal to L plus n plus 1 times m plus 1, and that's a problem, because here I am saying persistently exciting means rank is bigger than or equal to L plus n plus 1 plus 1 times m. Persistently on the other hand, this would imply that that same number is less than or equal to this. Sorry, there is a minus sign here. I missed the minus sign. Yeah, because this one is going to the other side. No, m minus 1. I think. Yeah, right. So here is this number. This number simultaneously is coming out to be bigger than or equal to this number and less than or equal to this number minus 1. That's impossible, right? How can a number be bigger than or equal to a number and less than or equal to a number strictly smaller than that number, right? Yeah. So if there are two numbers, I'm kind of saying that two integers x and y. X satisfies x is bigger than or equal to y. X is also satisfying x is less than or equal to y minus 1. That is absurd. This is not, the two cannot be simultaneously true. Okay? Because the two cannot be simultaneously true, that would mean, so this implies, so persistently exciting is something that we have already assumed, so we can't do anything about that. So therefore we have to live with this condition. What we can still make sure that doesn't happen is this. Yeah, that's the problem, that this intersection is 0. So therefore this implies B L plus n pop intersection r xi dot up to r xi to the n r xi. This is not equal to 0. So that means there exists some r xi polynomial which is in B L plus n pub, but this implies under controllability that r xi actually belongs to B L pub. Because of controllability, look back in our last lecture, because of controllability we have this, but that's a contradiction to what we had assumed. Or in other words, if r xi belongs to left kernel of HLW, that would imply r xi is in BL pub as well under PE condition, under persistency of excitation condition. Yeah. So if persistently exciting, this is what it is, which means left kernel of HLW is contained in BL pub. The other thing is always true, so therefore they are equal, which would mean column span of HLW is equal to BL. Lovely. This is the thing that we are after, right? So persistently exciting of order n plus L plus n plus 1 would imply that indeed this is true. If this, then that implies, remember this is a sufficient condition, yeah, that this is true. Okay, right? So that's how we get to this fundamental theorem or fundamental lemma of data driven control. Yeah, the consequences of this, some of them we will see in the next lecture, and then we will see how this idea of persistently exciting signals can actually be used to do things which are known as this data driven control, namely that you derive system theoretic properties of a system or you solve system theoretic problems like designing a controller which which makes the closed loop system satisfy desired properties. How can those things be achieved without actually doing a modeling of the system, without actually finding out a model for the system? Yeah, that's the basic idea, the philosophy behind data driven control. Yeah, this and a few more things is what we are going to see in the next lecture. Till then, take care.